Hi, this is Tzvi Rosen, and in today's lecture we'll be talking about graded rings and modules, and this includes bits and pieces from Chapter 10 and Chapter 11 in Atiyah-MacDonald. First we'll introduce the topic and what a graded ring and a graded module are. Then we'll talk about the Poincaré series and the Hilbert function, and we'll prove that they are respectively a rational function and a polynomial under the right conditions. Okay, let's start with the graded ring. A graded ring is a ring A together with a family AN, where the n's are indices starting at 0, going up 1, 2, 3, etc., of subgroups of the additive group of A, with A equals the direct sum of the AN, taking n equals 0 to infinity, and also satisfying the condition that AM times AN is contained in AM plus n. Okay, so if you take an element from the M piece and an element from the N piece and you multiply them together, they land in the M plus N piece. I'll also ask you to note that A0 is a subring of A, because when you multiply it together, right, if A0 times A0 has to be contained in A0 plus 0, but that's obviously just A0. Similarly, each AN is an A module because if you multiply A0 by AN, that still stays in AN plus 0, which is AN. So that tells you that AN is closed under multiplication by elements in A0. Okay. Let's discuss a couple of examples of graded rings. First, there's a trivial grading. So if you take A to be any ring, so we're going to define A0 to be the 0 graded portion of this ring. And then for n greater than 0, we're going to let AN just be equal to the 0 group. Okay? So clearly, if you take, so the direct sum of the AN is just equal to A0 plus a lot of zeros. So it's equal to A0, but that's equal to A, so that works. And if you take AM times AN, so if either of these is not equal to 0, this is just going to be equal to 0. So m is greater than 0 or n is greater than 0. But that's also equal to am plus n. So that's still respects the grading, and this is called a trivial grading because it doesn't really give us any insight into any structures here. You're just kind of satisfying the definition of the graded ring without really getting anything from it. But a different object where we can get something nice out of applying this grading is the polynomial ring in n variables. So here we can take AN to be the degree n homogeneous elements, homogeneous polynomials in A. Okay, so an example of a homogeneous element, okay, so would be x1 squared x2 plus x3 cubed minus x1, x2, x3. Okay, every sum end here has degree 3, assuming we're letting each variable have degree 1. Okay, whereas non-homogeneous would be something like x1 cubed plus x1, x2. Okay, here the degrees are different, so it's not homogeneous. Okay, so this, if you want to think about why this satisfies our requirements for a graded ring, so we need this to be equal to the direct sum of all of the ANs, where n goes from 0 to infinity. And indeed, given any polynomial, you just take it into its parts of different degrees. Okay, so you can consider this as a sum of the n graded part and the n minus 1 graded part, etc., all the way down to the 0 graded part, which is elements of k. Okay, as for whether am times an is contained in am plus n, that's a direct consequence of degrees of monomials being additive. So if you multiply x cubed by y squared, the monomial that results is degree 5. Okay. Now let's look at graded modules. So we're going to let A be a graded ring, just as we defined just now. A graded A module is an A module M together with a family Mn, where n, again, takes indices 0, 1, 2, 3, etc., of subgroups of M, where M is equal to the direct sum of Mn, n going from 0 to infinity. And when you apply the multiplication, the A multiplication on Mn, if you restrict to the M graded part of A, okay, keep in mind this is the M graded part of A, then that will land us in the M plus n graded part of M. Okay? So again, you have to keep in mind, in terms of why this definition isn't perfectly analogous to the graded ring definition, well, you don't have multiplication of module elements by each other, so you need to have multiplication by elements of the ring. But multiplying elements of the ring by elements of the module gets you into the right graded part of the module. And just as before, with an, we had that an is an A0 module, so too mn is an A0 module for all n. Okay, because A0 times mn must be contained in, mn plus 0, which is mn. Okay, so multiplication by elements in A0 preserves that module. Okay, we mentioned homogeneous elements in terms of homogeneous polynomials, but if we're in the context of a graded module, so a homogeneous element in a graded module M is an element in one of those subgroups. Okay, and indeed, you can always decode, just as we did with homogeneous polynomials or non-homogeneous polynomials translating to a sum of homogeneous polynomials, we can always translate any element of our module into a sum of homogeneous elements. So, given x in M, we can write x equals the sum of ai xi, even just xi, I equals, or I in some finite index set I. Okay, so I contained in the natural numbers is some finite index set. And we're taking xi to be contained in mi, thus homogeneous elements. Okay. Now we'll state a theorem about Noetherian graded rings. Okay, so we've defined graded rings, and we can prove this nice relationship between Noetherianity of the ring at large and of the zero graded part of the ring. So let's assume A is a graded ring. Then the following are equivalent. First, A is a Noetherian ring. Second, A0 is a Noetherian ring, and A is finitely generated as an A0 algebra. Okay. So again, we're saying A Noetherian is equivalent to the 0 graded part being Noetherian and the whole ring being finitely generated. So going in one direction is relatively easy, actually. So if we assume the second condition, then the first condition follows. This is a consequence of the Hilbert basis theorem. When you have a Noetherian ring, and then you have a finitely generated algebra over that ring, Hilbert basis theorem tells us that that's also Noetherian. Going the other way is a bit harder, but it's not too bad. Okay, so we're assuming that A is Noetherian. Okay, we're going to define A plus to be all of the homogeneous, all of the graded parts of the ring except for the 0 graded part. So this is n greater than 0, A sub n. Okay, so based on the rule of multiplication in this graded ring, A plus is an ideal. So we can pass to the quotient A mod A plus. Okay, but because A is equal to the direct sum over all the indices, we know that A0 is equal to A mod A plus. Okay, and since we have a quotient of a Noetherian ring by an ideal, this will also be Noetherian. Okay, but we need to prove the second part as well, that A is finitely generated as an A0 algebra. Okay, so at this point, we want to prove A is finitely generated as an A0 algebra. Well, we know that A is, so we know that A plus is finitely generated as an ideal of A. And that's a consequence of A being Noetherian. Okay, so that means that it's going to be equal to the ideal generated by x1 up to xr, some elements in the ring. If we consider the A0 algebra generated by these elements, that's definitely going to be a subalgebra of A. So we can think about what that looks like. So let's let A prime be equal to A0 adjoin these elements. Okay, so clearly this is a subring of A. Now, if we can show that A is also a subring of A prime, then that will give us that they're actually equal, in which case A is a finitely generated A0 algebra. Okay, so we're going to do this by showing for one index at a time that AN is contained in A prime. Okay, and we're going to start, and this is claimed to be true for all n. So we'll argue by induction. Okay, let's start with the base step, which is pretty trivial. So A0 is obviously contained in A prime. So the base step is proved. Okay, now for the induction step, so we're going to assume that A sub n is contained in A prime Let's make it a sub k. It's contained in A prime for k strictly less than n. Now we want to show it's true for an as well. Okay, so let's consider any element in A sub n. Okay, so we know that A sub n is part of the ideal A plus. So we know that x is in A plus, which means that we can write x as a finite A0 linear, or finite A linear sum of the elements x1 through xr from the previous slide. So this will be ai xi, where I goes from 1 to r, and ai is in A. Okay, but now let's think about what the degrees of the AI are, what graded parts of A they have to be in. So we know that xi is in A plus for all I. That means that if x is in an, then A sub I has to be in A sub n minus k, let's make ki, where ki is the grading of xi. Okay. But by our induction hypothesis, that implies that ai is in A prime. Okay. And since xi is used to generate A prime, they're obviously in A prime as well. So that means that x must be in A prime, and that proves the induction step, which proves that we have containment of A in A prime. That tells us that A is equal to A prime and A is finitely generated. Oh, as an A0 algebra. Okay. Okay, so we've spoken a bit about graded rings and modules, and now we can get to the Poincaré series. This is a picture of Henri Poincaré, incredibly prolific mathematician in wildly different areas: number theory, algebraic topology. You'll see his name come up everywhere, including here in commutative algebra. Okay, so let's start by defining a Poincaré series. If we take A to be a Noetherian graded ring, just like the one we discussed in the last theorem, generated over A naught by elements x1 through xs in degrees k1 through ks. And we take M to be a finitely generated graded A module, and lambda an additive function on finitely generated A0 modules. Then P of MT, the Poincaré series, and sometimes this is called the Hilbert Poincaré series, but so many things are named after Hilbert that we will probably continue to omit this. And I think Atiyah-MacDonald do call it just a Poincaré series. This is defined as the sum for n greater than or equal to 0 of lambda of mn times t to the n. So you evaluate this additive function at the n graded part of the module m, and then you kind of attach it to a power of t to the n. So for people familiar with generating functions, it's like a generating function for the value of lambda at each n graded part of our module. In terms of what lambda will expect in general, a good thing to kind of keep in mind for your intuition is if A is, let's say, a field. Sorry, if A is an algebra over a field, then we might take lambda of mn to be the dimension with respect to k of mn. That's an example of the type of additive function we'll use. And you can carry that through as guiding your intuition throughout. Okay. Let's look at some examples of what the Poincaré series would look like for specific graded rings. So the trivial graded ring, again, you'll recall that this is a naught equals a and an equals 0 for n greater than 0. Well, the Poincaré series, looking up here again, okay, we're going to assume that a0 is Noetherian. But thinking about what if we want to consider this as a module over itself, the 0 graded part is the whole ring. So we'll take that to be just 1 because it's dimension 1 over itself, let's say. And then, or let's call it lambda of a as a module over itself. And that's times t to the 0, but then everything else obviously gets just a 0 coefficient. So this is going to be lambda of a. Okay, and for example, this could be the constant 1. So as Poincaré series go, this is not particularly interesting. But if we take a polynomial ring in one variable, what does this look like? So if we're taking lambda of mn to be equal to dimension over k of mn, as we said before, then let's think about what the graded pieces here look like. And we're giving it the standard grading where you just take the degree of the power of x. So we have in degree 0, there's just k. So k adjoin x is equal to k, and then add to that kx, you get kx squared, etc. Then obviously in each degree, you're only getting a single copy of the field. So that tells me that this should have constant degree 1, which tells me that p of let's just say k adjoin x as a module over itself, t is equal to 1 plus t squared, etc. And if you remember your calculus 2, this is going to be 1 over 1 minus t. Okay? Let's continue with our examples. Now what happens if we adjoin more variables? So based on our last example, the degree of the monomial is what will determine which part of which graded part of the ring it lands in. And if you wanted a basis for a specific graded part, you could take all of the monomials in that degree. So for degree s, let's say, the monomials x1 to the a1 up to xn to the an, where a1 plus up to an equals s, span the as, the s graded part of the ring, if we're calling this a. So how many such monomials are there? Well, this is a combinatorics problem. You can use the stars and bars approach to get that So for instance, we needed to add up to s. So we're going to place our s stars. Okay, and then you want to put the n bars, or really the n minus 1 bars, to delineate the n categories, like where are these s stars landing. And so we have n minus 1 plus s different locations to put our bars. So this ends up becoming, by stars and bars argument, the number of monomials will equal n plus s minus 1, choose n minus 1. Okay. So the Poincaré series P of AT is going to be equal to the sum of n plus s minus 1, n minus 1, t to the s, where s goes from 0 to infinity. And if you work out the manipulations, this is going to be equal to 1 over 1 minus t to the s power. Okay. Here's one slightly different example, just so we can get a sense of the different types of expressions we'll find. So let's consider the case of two variables. So if we want a basis for just k adjoin x, y, we can think about each power. So each exponent vector has two coordinates, right? The power of x and the power of y. So those can live in this quadrant. And in particular, they'll live on the integer points in the positive quadrant. Okay. And the degree s part of this, so the degree 0 part is this, the degree 1 part is this. You can get the fixed degree parts by taking these diagonal lines. Okay? So if we wanted to know about k adjoin xy mod x squared y squared, we've got to think about which monomials now no longer are allowed in our computations. So x squared, the fact that you're modding out by x squared y squared means that x squared y squared can't divide any monomials. So here's x squared y squared. What we're saying is anything that is a product of that is going to be omitted. Okay? So now instead of the full quadrant that we had before, now all of our fixed degree pieces are going to have kind of two pieces here and then two more pieces here. Again, two pieces here, two pieces here. So what we're going to be looking at is, so this is going to be equal to the sum, where n goes from 0 to infinity, of dim k of mn, this is our m, times t to the n. So this will look like 1 for the 0 degree part, plus 2t plus 3t squared plus 4t cubed, right? Because this is the 0, 1, 2, 3, 4, 5 graded parts. And then so this seems to be stepping up, but then when we get to the degree 4 part, we're going to get 4 again, plus 4t to the 5th, plus 4t to the 6th, etc. Okay? And if you'd like to figure out what that means in terms of if there's any way to summarize this in a shorter form, right? Besides just listing it's 1, 2, 3, and then all 4s. Another way to do this would be to say, well, listen, if we had started with the whole plane, so then the corresponding Poincaré series would be p k adjoint x, y. T is going to be equal to 1 over 1 minus t squared. Okay, because we get the, just as in the case with n variables, if you set n equal to 2, that's, or, oh, you know what? There's some confusion of n and s in here. Please forgive me for that. But we get a quotient, we get 1 over 1 minus t squared in this case. And then we can also consider the red part here. So p of x squared y squared times k adjoint xy t, well, that's going to be equal to, it's really just the same thing, but shifted up by 4. So that's t to the 4th over 1 minus t squared. So if for Rm, what that tells us is p of mt is going to be equal to 1 minus t to the 4th divided by 1 minus t squared. And you can check the arithmetic there to make sure that the expansion of that rational function agrees with the terms that we computed. Okay. Hopefully that gives you a flavor for computing explicit examples of Poincaré series. Now we'll prove an important theorem about them. So specifically, the Poincaré series is a rational function. If we take A to be an Arithurian graded ring generated over A0 by elements x1 through xs in degrees k1 through ks, and M a finitely generated graded A module, and then lambda is again an additive function on finitely generated A0 modules, then P of MT, the Poincaré series, which we defined as the sum for indices greater than or equal to 0 of lambda of mn t to the n, is going to be equal to f of t divided by the product from I equals 1 to s of 1 minus t to the ki. So you're taking 1 minus t raised to the grading of that generator. And that f of t is going to be a polynomial with integer coefficients. Okay, and looking back, you can see that it happens to be true of each of the examples we computed. Even in this case, it just ended up being 1, but that's the empty product. You're dividing by the empty product since it has no generators over the A0. Okay, let's prove the theorem. We argue by induction on the number of generators of A over A0. Okay, so we're arguing by induction on the number of generators, let's call it S of A over A0. Okay, so in the base case, we'll take S to be equal to 0 so that A is just equal to A0. Okay, and that means that if M is a finitely generated A module, then it's also a finitely generated A0 module. Okay, but if M is a finitely generated A0 module, that means that we can write it down like this. But depending on the grading of each of these xi's, the corresponding Poincaré series is going to be eventually 0 because multiplying A0 by any item of fixed grading, any element of M of fixed degree, is going to give you, it's going to be bounded in terms of its degree, so this means that this is polynomial, okay, which is exactly what we want for the case s equals 0, because we want to have a polynomial in the numerator and s many factors in the denominator. Okay. Now we want to prove the induction step. Okay, we want to suppose it's true for k less than s. Let's make it r less than s. We want to show that it's also true for s generators. Okay. Well, let's consider the following sequence, following exact sequence. Zero maps to Kn, maps to Mn, maps to Mn plus Ks, and this map is going to be multiplication by xs. Okay, the s generator that we're looking to learn about. Okay, then this goes to ln plus ks to 0. So kn is the kernel of the map, which is multiplication by xs, and ln plus ks is the co-kernel of that map. So it's everything is nicely well defined. Now, because we have that lambda is an additive function, and by examining k and l as quotients or as submodules of M, we know that all of the modules involved here are finitely generated. We can apply lambda to every module in this sequence, and we'll get that lambda of Kn minus lambda of Mn plus lambda of Mn plus Ks minus lambda of Ln plus Ks equals 0. Okay, so this is a nice relationship among the values of lambda on all of these modules. So now if we consider, if we sum this over all values of n, so what we get, and then also multiply by appropriate powers of t to the n, what we'll get is p of knt minus p of, sorry, this should just be p of kt, minus p of mt plus, and now here we have to be a bit careful, this is going to be t to the ks times p of mt minus t to the ks times p of lt equals 0. Though we actually should be a bit careful here, but because there's some funny business at the earlier parts of the series, because we can't, we're going to miss some of the indices here because we start at Mn plus Ks as well as here. So we want to include a correction term for a few small powers of t. So let's add a polynomial here, g of t. Okay. So now we want to find an expression for p of mt. So let's put everything else, let's put the p of mt's on the other side of the equation, and we'll get that 1 minus t to the ks times p of mt is equal to what remains, which is p of kt minus t to the ks p of lt plus, so let's write this down, p of kt minus t to the ks p of lt plus g of t. Okay. Well, what do we know about p of kt and p of lt? So these are, k and l are both annihilated by multiplication by xs, by this sth generator of the module, because just in terms of how it's defined, right? Kn is the sum, k is the sum of these kn's, which are the kernels of these maps that you get by multiplying by xs, and the l's are defined as the co-kernel of those maps. So multiplication by xs what also sends the elements of L to 0. So we can think about them as just these are modules over the subring generated by x1 through xs minus 1. Okay. Include that 0 graded part here. Okay, but applying the induction hypothesis, that means that P of kt and P of lt can both be written as polynomials, can be written as integer coefficient polynomials divided by 1 minus t to the appropriate powers. H of t divided by product up to s minus 1 of 1 minus t to the ki. Okay. And so then what we have on the left-hand side of the equation is 1 minus t to the ks times p of mt, and then we have this sum of rational functions, both of which have the 1 minus t to the ki for all of the other values of ki. So this implies that p of mt has the desired form. Okay. So that proves the theorem that the Poincaré series, given the right conditions, it's a finitely generated module over a Noetherian graded ring, that it has this nice form of integer coefficient polynomial divided by product of these 1 minus t to a power. Now we'll move from Poincaré series to the closely related concept of a Hilbert function. Okay, we'll use the same setup. We have A, which is a Noetherian graded ring. And as we know, that's equivalent to being finitely generated over a Noetherian ring. And M is a finitely generated graded A module. And lambda is an additive function on the class of A0 modules. Okay, and you can think about the graded parts as being finitely generated. Oh, this should also be finitely generated. Finitely generated A0 modules, like the graded parts of M, which are A0 modules. Then the Hilbert function lambda of Mn as a function of n, this is the Hilbert function. The Hilbert function of n. Okay, so you can think about this as the coefficients in the Poincaré series. Okay, let's look at some examples. Trivial graded ring considered as a module over itself. The Hilbert function, which is lambda of mn equals, let's say in the case that we're looking at a field, so dim k of m n. Okay, so then the Hilbert function here is just going to take the values, so f of n will be equal to 1 when n equals 0, and 0 for all other cases. Okay, so again, this is trivial graded ring where we take a equals k. So that we can avoid questions of rank of the module or whatever. Let's just think about simple dimension. Okay, now let's think about the ring of polynomials in one variable as a module over itself. And here too, we're going to take lambda of mn to be dimension over k of mn. Okay, so fn is equal to, well, here it's much more constant. Fn is actually equal to 1 for all values of n. Okay, so that's straightforward. Now we can think about this. Well, we saw before that if we're taking lambda of mn to be equal to the dimension over k of mn, this is the number of monomials. And you know what? Let's make this s, so it's a little less confusing. Number of monomials of degree n in s variables. So this is going to be equal to s plus n minus 1. Choose s minus 1, okay, because you're picking where to put your bars. Okay, and this is a nice polynomial function in n. Okay. We can look at this same example as we saw before. We saw that, again, taking lambda of mn to be equal to the dimension over k of mn, and thinking again about this picture with the diagonal lines, okay, how at first we have some, we have kind of the standard monomials, then at a certain point, so here we have x and y, this is x squared xy, y squared, here it's still normal, but then here is where we get our first forbidden monomial, and then everything up and to the right of it. So we're left with just 4 monomials in each subsequent graded part of the module. Okay, so in this case we had said that f of n is equal to 1, 2, 3, and 4, where this is for n equals 0, this is for n equals 1, n equals 2, and then n greater than or equal to 3. Okay. So there's some kind of piecewise behavior happening here. You have a few steps where things are a little off, but then it takes a form that it sticks with the rest of the time. And that's a behavior that is actually true of Hilbert functions in general, not just for rings as modules over themselves, but for modules writ large. And the theorem says that Hilbert function is polynomial, and what that should say really is eventually polynomial. Okay, and we have here the standard setup. If A is a Noetherian graded ring generated over A naught by D elements of degree 1, okay, and this is true also if we're not restricting it to be D elements of degree 1, but this makes the statement of the theorem nicer, or the conclusion of the theorem nicer. Then M is a finitely generated graded A module, and M is a finitely generated graded A module, and lambda is an additive function on finitely generated A0 modules. Then for n sufficiently large, well greater than 0, lambda of Mn is a polynomial in n of degree D minus 1. Okay, so D is the number of generators again. Okay, so we're going to get a polynomial function with this very clearly specified degree. How might we prove that? We're going to use the theorem about Poincaré series. So we know that for the module satisfying all of the conditions in the theorem, then we're going to have P of MT will be equal to some polynomial with integer coefficients, f of t, divided by product from I equals 1 to s of 1 minus t. Okay, and since we don't have distinct gradings here, we can forget about it as a product and just list it as a power, right? Because we're saying, we specified in the previous slide that all of the elements are generated, that the ring is generated in degree 1. So all of the generators have degree 1. Okay. So what does this look like? Well, f of t, we said, is integer coefficients polynomial. So it looks like a0t, sorry, it should be a k t to the k, where k equals 1 to n. And then what does 1 over 1 minus t to the s look like? This looks like, as we discussed before, this is the number of monomials of degree n in s variables. Or rather, let's use a different index. This is let's say d. So the number. So if we want d to be going from 0. Sorry, this should be also from 0. D to be going from 0 to infinity of d plus s minus 1. Choose s minus 1 times t to the d. Okay. And now what we want in order to determine the Hilbert function, so lambda of mn is going to be equal to the coefficient of t to the n in the product of these two terms. Okay, this times this, the product has a t to the n term, and we want to know what that will look like. Well, for that, I kind of want to give this a different letter. Let's make that m. Okay. So what is the coefficient of t to the n? Well, it needs to be the product of two things whose powers add up to n. So we have, this is equal to the sum of ak times d plus s minus 1, choose s minus 1, where k plus d is equal to n. Okay. But this is another way we could write this is as sum of a k times n minus k plus s minus 1, choose s minus 1, k goes from 0 to n. If n is less than m, then we're still missing some coefficients here, right? We won't get the full list of terms. Okay, so the function does not include every ak. Okay. But once we have n greater than or equal to m, all ak's are included and the Hilbert function is fixed as a polynomial. Okay, and in particular, looking at this formula, it's going to be an integer linear combination of binomial coefficients. Those binomial coefficients can sometimes not have integer coefficients, but they're always integer valued. Okay, so this will be an integer valued polynomial, possibly rational coefficients. This Hilbert polynomial, as well as the Poincaré series, will give us a lot of information when it comes to dimension, and we'll explore what dimension is and how this relates to cruel dimension of rings and dimensions of algebraic varieties in the next lecture. Thanks so much.